Beneath the vast, silent ice sheets of our world, a powerful force is waking up. For thousands of years, the crushing weight of glaciers has pushed down on the Earth's crust, holding ancient, dormant fault lines in a deep slumber. But as our climate warms and the ice melts, that pressure is being released. It's not just about rising sea levels. The very ground beneath our feet is becoming less stable, and sleeping geological giants are stirring. Today, on Fun Facts Online, we're exploring the icy veins of the Earth and how glacial melting is triggering earthquakes and a cascade of other hazards across the globe. So how does melting ice cause the ground to shake? It's a double-edged sword, involving two distinct but connected processes. First, there's something called Glacial Isostatic Adjustment, or GIA. Imagine placing a heavy book on a soft mattress. The mattress sinks. When you lift the book, the mattress slowly bounces back to its original shape. The Earth's crust acts in a similar way. Under the immense weight of an ice sheet, the land is depressed. As that ice melts away, the land rebounds. This isn't a gentle, uniform process. As the crust flexes and bends, it puts immense stress on pre-existing weaknesses, the fault lines. It essentially unclamps them, making it far more likely for them to slip and trigger an earthquake. Scientists have found clear evidence of this in places like Fennoscandia, which includes Norway, Sweden, and Finland. As the last great ice sheet retreated from that region, it triggered massive earthquakes, some estimated to be as powerful as magnitude 8. These weren't small tremors. They were powerful enough to leave visible scars on the landscape that you can still see today. But GIA is the long game, a process unfolding over thousands of years. There's a much more immediate and insidious threat: the meltwater itself. We're talking about staggering volumes of water. This water creates complex plumbing systems within and beneath the ice, forming rivers that flow at the glacier's base. When this water reaches the bedrock, it can seep deep into cracks and fissures within a fault zone. This is where a concept called pore pressure comes in. Think of a sponge full of water. The pressure of the water inside the sponge's pores pushes outward. Similarly, when meltwater fills the pores in the rock of a fault line, it pushes the rock apart from the inside. This pressure counteracts the friction that holds the fault locked in place. It effectively lubricates the fault, making it easier for the two sides to slip past each other. For a fault that's already stressed and close to its breaking point, this extra push from water pressure can be the final nudge that triggers an earthquake. We're seeing this happen right now in the Alps, where intense glacier melt has been linked to a rise in micro-earthquakes as water infiltrates and weakens the region's fault lines. Let's look at some real-world examples. Southern Alaska is a perfect natural laboratory for this phenomenon. It's home to enormous glaciers, but it also sits on the boundary of the Pacific and North American tectonic plates, making it one of the most seismically active places on Earth. For centuries, the weight of the ice helped clamp these faults down. But now, as Alaska's glaciers melt at an alarming rate, that stabilizing force is vanishing. A landmark study looked at the massive magnitude 7.8 earthquake in Lituya Bay back in 1958. That quake triggered a tsunami of unbelievable proportions. The study found that the epicenter was located right near an area that had experienced the most significant ice loss. The theory is that the land's rebound from the melting ice, the isostatic adjustment, added stress to the fault and helped set the stage for that catastrophic quake. More recent research has backed this up, suggesting that glacial rebound has influenced the timing and location of many earthquakes over magnitude 5.0 in Alaska in the last century. The European Alps are also feeling the heat, literally. The mountain range is warming at about twice the global average, causing a dramatic retreat of its glaciers. This has been followed by a startling increase in seismic activity. In the Mont Blanc Massif, for example, the frequency of micro-earthquakes has shot up tenfold since 2015. Scientists believe this is due to meltwater seeping deep into the rock, increasing that pore pressure we talked about, and weakening the faults. While these tremors are small for now, they are a clear warning that the region's stability is changing. And if we look back at Fennoscandia, we see the echoes of the last ice age. The massive fault scarps there are a stark reminder of the power of post-glacial rebound. They were formed by magnitude 8 earthquakes as the ice retreated 10,000 years ago. It's a sobering look into the potential long-term seismic consequences of our current era of rapid ice melt. Even the sleeping giant, Antarctica, is stirring. This continent holds the majority of the world's fresh water in its vast ice sheets. Research shows that as this ice thins and retreats, the underlying crust is responding. Ancient rift systems, particularly in areas like the Ross Sea, are showing an increased potential for fault reactivation. The immediate human impact there is low due to its remoteness, but the big concern is the stability of the ice sheet itself. An earthquake could potentially destabilize large sections of the ice, accelerating its slide into the ocean and having massive global consequences for sea level rise. But the danger doesn't stop with the shaking ground. The interplay between melting ice and earthquakes can unleash a cascade of secondary hazards. One of the most terrifying is a GLOF, or Glacial Lake Outburst Flood. As glaciers retreat, they often leave behind depressions that fill with meltwater, creating huge lakes. These lakes are often dammed by nothing more than unstable ridges of loose rock and sediment left by the glacier. An earthquake can be the perfect trigger to shake that unstable dam apart. When it collapses, it releases a sudden, massive torrent of water, rock, and ice that can travel for miles downstream, destroying everything in its path. The Himalayas are a major hotspot for GLOFs, with a growing number of these hazardous lakes forming as glaciers shrink. A GLOF in Nepal a few years ago washed away a key bridge and damaged hydropower projects, showing just how destructive these events can be. Then there are landslides and avalanches. Glaciers don't just carve valleys. They also act as a buttress, propping up the valley walls. As a glacier retreats, that support is removed, leaving behind oversteepened, unstable slopes. These slopes are primed for failure, and an earthquake can be the final straw that triggers a massive landslide or rock avalanche. This is dangerous enough on its own, but it can also create a domino effect. Imagine a massive landslide crashing into one of those unstable glacial lakes. It can displace a huge amount of water, creating a wave that overtops the dam and triggers a GLOF. It's a devastating combination of hazards with far-reaching impacts. So what can we do? Predicting the exact time and place of an earthquake is still beyond our reach, but scientists are not sitting idle. They're using a suite of cutting-edge technologies to monitor these regions. Networks of seismometers detect even the tiniest ice quakes, giving clues about what's happening beneath the ice. High-precision GPS stations on glaciers track their movement, while satellites using a technique called INSAR can map ground deformation over huge areas, spotting the slow uplift from isostatic rebound and identifying areas where stress might be building on faults. Scientists even use subglacial probes and ground-penetrating radar to see what's happening at the base of a glacier, measuring water pressure and mapping hidden river systems. With this data, we can create better hazard maps to identify the areas most at risk. For threats like GLOFs, we can build early warning systems. These use sensors to detect a sudden rise in lake level or ground vibrations from a landslide, triggering alarms that give downstream communities precious time to evacuate. This information is also crucial for better land use planning, ensuring we don't build critical infrastructure like dams or settlements directly in the path of these known hazards. The reawakening of these long dormant fault lines is a profound and unsettling consequence of our warming planet. The complex dance between ice and water that has shaped our world for eons is being thrown into chaos, and we are just beginning to understand the geological fallout. While science is racing to keep up, the pace of change is rapid. This means we must learn to adapt to a world on increasingly unsteady ground. It requires investment in science, in monitoring, and in proactive strategies to protect vulnerable communities. Ultimately, the story being written in the ice and stone of our planet's frozen frontiers is a cautionary tale. It underscores the urgent need to address the root cause of the problem: climate change. The icy veins of the Earth are sending us a clear message, and it's one we can't afford to ignore.